Thanks. I should maybe adjust that title, which, given the abstract, you can imagine that I'm not just going to talk about schemes, although most of the talk will be about schemes. But I should say the talk is really going to be about Drinfeld lemma for schemes and perfectoid spaces, because at the end, one of the key applications I have in mind uses perfectoid spaces rather than schemes. So maybe I should start with the sources for this. So this is mostly a recap of something I explained in one of my lectures at the 2017 Arizona Winter School, specifically the last lecture. So that's a good place to read about this with a lot more details than I'll actually fill in here. There are also two papers that will come up. One is about Drinfeld's lemma for perfectoid spaces per se. And then one is about an application in p-adic Hodge theory, which I'll talk about at the end. Hopefully I'll have a little bit of time for that. With two co-authors that I'll refer back to later. OK, so let me start by talking about fundamental groups. Let me just do this for schemes at the moment, and then when we get to perfectoid spaces, it'll work kind of the same way. So part 1 is pi 1. OK, so for X a scheme, right? To talk about a fundamental group of a space, you generally think of it as being related to covering, as sort of unramified coverings of it. Well, what is the notion of an unramified covering in the world of schemes? Well, generally the best we can do is talk about finite Étale coverings. I mean, you can talk more generally about Étale coverings that are not finite, but for the purposes of defining pi 1, I'm just going to talk about finite Étale coverings. So I'll write f et of x be the category. This will be the category of finite Étale coverings of x. If you prefer to have this be in the category of finite Étale schemes over x, I think everything I write down will remain true. But I think I'm going to take it to be coverings. So yeah, so they're actually finite Étale. So I should really say finite Étale surjective morphisms to x in the category of schemes. And the surjective here, as I said, the surjective here is not really necessary. I would get the same answer as if I didn't have that there. But OK, so these are like covering space maps, mapped down to x. And to talk about the fundamental group of x, well, I'll need a base point. So let x bar be a geometric point of x, which is to say spec of an algebraically closed field. Maybe I'll write k bar to emphasize that it's, well, actually I'm not going to remember to do that because it's not in my notes. So let me just say spec of a field, which is algebraically closed, mapping to x. So then one defines the fundamental group of x with respect to this geometric point as the automorphisms of a certain functor, the fiber functor associated to x bar. So omega x bar is the functor from finite Étale guys over x to sets, taking an object y to, well, you take y, you base change from x to this geometric point. Now you have something finite Étale over a geometric point. Well, the only finite Étale algebra over an algebraically closed field is a direct sum of copies of that field. So this splits as a disjoint union of copies of x bar. So I don't really lose any combinatorial information by just passing to the underlying set. And so that's what I'm going to do. So I take y, and I'm taking its set theoretic fiber over x bar. So that's this functor, and then automorphisms of that means, well, natural transformations from this thing to itself. So, well, this is just basically a fancy way of coding Galois theory. For example, if x is spec of some field, I'm going to call it something other than k, k0, then what you're doing here is taking the absolute Galois group of k0. And more precisely, what you're doing is you are taking, so the geometric point it defines an inclusion of k0 into an algebraically closed field. What you're doing is taking the separable closure of k0 inside that algebraically closed field, and you're taking the automorphisms of that over k0. So it's that particular copy of the absolute Galois group, in case you want to be more precise. I will probably not be that precise for the rest of the talk. In these references, things are precise, but for the purposes of exposition, I will probably be sloppy and forget to write base points most of the time. But if you're ever confused, ask me, and I will disambiguate. OK, so so this is a notion of, so this is sometimes called the Étale fundamental group, because it's connected to this notion of an Étale covering. But to be safe, I'm going to call this the profinite fundamental group, because in certain contexts you might be willing to consider, especially when x is not normal, you might be willing to consider covering space maps that are not finite. For example, if you have like a nodal curve, then you might be willing to consider sort of a helical covering of this thing. Right? You can have a covering of this where you have like a bunch of copies. Actually, maybe it's easier to draw this if I take what's called the banana scheme, 2 copies of P1 that cross at 2 points. So right, this has an infinite Étale covering. It's basically the version of the standard helix in algebraic geometry, except we don't have a circle. So we use this thing. And now that I've drawn this, you could see how to do the corresponding thing with a nodal curve, which I'm just not very good at drawing. So you could imagine some situation where you want to consider this kind of thing as an infinite covering space over this thing. But for the purposes of this talk, I'm only going to allow finite Étale coverings, or pro covers built out of finite Étale things. So this thing is automatically going to be right. If you sort of this thing, an automorphism of this thing is some kind of family of coherent permutations of these sets. So with a little bit of effort, you can show that it's a profinite topological group. But since I'm only going to consider this kind of fundamental groups, I'm not going to put a subscript. I'll just write pi1. OK? So generally, it doesn't make sense to talk about this unless x is connected, because if x is not connected, then you're really only seeing information about the connected component where this point lands. So generally, I'm only going to want to consider this when x is connected, but yes, technically I didn't have to put that in the definition. OK. So that's what pi1 means. So let me tell you something about how fundamental groups of schemes work in characteristic 0, which is quite compatible with our geometric intuition, and in fact, ultimately depends on that. So here's a fact, which you can read this in the Stax project somewhere. So let k to k prime be an inclusion of algebraically closed fields of characteristic 0 then for any scheme x over k, if I take the finite covers of x, those are the same as the finite covers of the base change of x from k to k prime. So the fundamental group does not depend, so these finite covers do not depend on the choice of an algebraically closed base field. Of course, I have to say algebraically closed here because otherwise I'm picking up the Galois group of this field. So that clearly needs to be removed. So I assume both of these are algebraically closed, and then somehow this is only seeing kind of geometric stuff, and the geometric stuff does not change when you change the base field. That's what this is saying. And in particular, if x is connected, then pi1 of x to pi1 of xk prime is an isomorphism for base, where I'm starting to drop base points, but you can sort of imagine what the base point should look like. OK. So as I said, you can read this somewhere in the Stax project. So let me not actually give the complete proof, but let me give you the basic idea. So I can do various things. One thing I can do is reduce to the case where x over k is a finite type, because right, I'm trying to prove this equivalence of categories. I can do this locally on x, for example. So I can assume, for example, x is affine. And then, well, if x is affine, it's spec of some ring, some k algebra. And so I use the fact that if I have a ring which is a colimit of some other rings, then category of finitile R algebras. So, OK, I mean a finitile of spec R, but is the limit of finitile categories of these RIs, just because, right, when you write down a finitile R algebra, it involves some finite number of ring elements. So you could sort of find it over one of these things, and likewise for morphisms between them. Sort of this is a standard technical trick in foundations of algebraic geometry. So by this kind of argument, I can assume x over k is finite type. With a slightly more work, I can also assume that with a little more work, I can assume it's smooth. Let me not get into that. And I can assume by sort of a standard, right? There's a sort of standard thing in algebraic geometry that every algebraically closed field of characteristic 0 behaves like C. So I can assume, say, that k prime is C for the purposes of proving a statement like this. Because again, at any given moment, you only refer to finitely many elements of k, and so you could sort of stick those inside C. And then what you do is you compactify x, and then so by compactifying, you somehow reduce to the case where x is proper. Somehow, so this uses the fact that all ramification is tame. which is a thing, of course, that's going to fail in characteristic P. So this is the first point at which characteristic 0 is seriously being used. And then you use something else, which in principle is a characteristic 0 thing, which is that I show that for x proper, that what I'm getting, that the pi1 of x is actually the profinite completion of the topological pi1 of the the associated topological space of the base change to C. So, and this is by the Gaga theorem, right? So if you have a topological cover of this thing, you can give it the structure of a complex analytic manifold, and then the morphism from it to the x actually has to come from a morphism of schemes, basically. Right? You apply Gaga to the push forward of the structure sheaf.
So is that for xk prime?
Yeah. So k prime is, right, I took k prime. I put myself in the situation. Yeah. So this is.
No, you wrote pi1 of x.
Yeah. So pi1 of x is, right. So pi1 of x, yeah, if you want to write k prime here, you could. But the point is that it sort of doesn't change. What you're really using is that whatever k is, this thing is the same as the profinite completion of the pi1 of the complex. So you sort of get both things at the same time. Yeah. So in fact, this actually remains true without assuming proper, as long as x is a finite type, essentially, because the only ramification is tame, and you can kind of keep track of it. I should remind you, I'm not going to write this on the board because this is tangential, but this is worth pointing out for if you haven't seen this before. Right, when you take, if you have a x over like a number field, say, you could say, well, I can stick that number field in C and then base change C and then take the topological pi1. I'm claiming that the profinite completion of that is something that's intrinsic to x, and therefore doesn't depend on the embedding of that number field into C. You can ask whether the actual topological pi1 of the base extension to C is itself determined by x, and the answer to that is no. There are famous examples that go back to Serre that show that the pi1 of the base extension to C does in fact depend on how you stick the base field into C, but its profinite completion doesn't. So, as I said, that's not directly relevant to what I'm saying, so I don't write it on the board, but if you haven't seen that fact before, you should know it. Corollary. So using this, you can relatively easily deduce that let K be an algebraically closed field of characteristic 0. So you might as well think C here. So assume that x is, so to speak, nice, which this is just for some technical argument in the proof. I need it to be quasi-compact and quasi-separated. Right? Quasi-compact means, of course, that the underlying topological space is quasi-compact. Quasi-separated means that the diagonal is finite or something. Yeah, the diagonal is quasi-compact. Sorry. Yeah. So I want the x to be quasi-compact, which is the same thing as saying x, the morphism from x to k is quasi-compact. Field is affine is quasi-compact, and quasi-separated means that the diagonal is a quasi-compact morphism. But anyway, okay. I'm just going to write nice to me. Well, I guess people write QCQS for the conjunction of these two things. But you should read this as a funny way to spell the word nice. Assume x is nice, then you only need one of the two to be and then let y be any scheme over k. So x is a scheme over k, which is nice. Y doesn't have to be nice, although in practice you typically, or in the case where both of them are nice. Then when you take the fiber product over k, that commutes with taking the product of fundamental groups. Okay. So this QCQS condition comes when you try to argue that, well, I don't want to say too much about where it comes in. It's some annoying technical part of the proof where you consider this thing as a fibration over x, and then you're trying to you want to write down the homotopy fiber sequence for that, and in order to actually analyze that, you need QCQS at some point. Okay, now part 3. What happens in characteristic P? Well, things go a little bit haywire. Well, they don't completely go haywire. So this corollary remains true if you if you add the condition that x over k is proper. So in the last corollary, if x to k is proper, then this still works in characteristic P. But otherwise, it fails miserably. And I've already hinted as to why. Right? I alluded to the fact that we took advantage over there of the fact that all ramification in characteristic 0 is tame. So if you work with, so to speak, a version of pi1 where you only allow some kind of tamely ramified morphisms, you have to straighten out what that means when you're not talking about schemes of finite type or something. But so if you kind of work with a tame pi1, then you can salvage this kind of statement or that kind of statement. But otherwise, things fall apart. So of course they fall apart in more or less the first example you can think of, which is an affine line. So, right, and the reason for that is that we know how to write down the continuous homomorphisms from pi1 of x to z mod p by Artin-Schreier theory. So this is the Artin-Schreier construction. This is canonically isomorphic to, so if I call the variable t, then what I do is I take the additive group of the base ring, kt, and then I take the co-kernel of the map Frobenius minus 1. And theres a natural bijection between these two things, right? What you do is you say, well, right, this comes from, right, if I take the map phi minus 1 from here to here, the kernel of it is fp, and this thing turns out to be, so when I pass to Étale sites, this actually turns out to be surjective. So if instead of writing this, what I should really write is, if I take the constant sheaf fp, and then I take the constant sheaf on the Étale side of x, and then take phi minus 1 Sorry, the structure sheaf, not the constant sheaf. So now, on here, phi minus 1 is actually surjective, so this is an exact sequence. And when you take the long exact sequence, this is the h1 term that sits down here, and the h1 term that sits here is 0, so you're just getting the co-kernel of this map. Right, and the point is that this definitely is not independent of k, right? Because this is some, except for if you ignore the constant term, you get a bunch of k vector spaces corresponding to the powers of t that are not, whose exponents are not divisible by p, and those certainly get bigger as you increase k. So this is not preserved under enlarging k. And so once you know about this, well, if you're a normal person, you just throw up your hands and say, well, I can't say anything. Thankfully, Drinfeld is not a normal person. So Drinfeld had an idea about what to do about this. And I like to say that if you sort of know enough algebraic geometry, you would be dissuaded from trying to do anything about fundamental groups of schemes of characteristic P. But Drinfeld was quite young when he did this, so he in some sense didn't know any better until he was armed with the kind of the courage of inexperience to do something where no reasonable person would have tried. He succeeded. So Drinfeld says, OK, let X be a scheme over Fp, and let K be a field of characteristic P, algebraically closed. So what does Drinfeld say? He says, well, I'm going to compare the finite tall schemes over X to the following. So I'm going to base change from Fp to K, but then I'm going to divide by the Frobenius on K. So what do I mean here? I mean this. So right, since X is. So what do I mean by this? I mean, so I'm doing this division in the sense of stacks, but what I mean about this category, these are so to speak phi k torsors in finite tall xk schemes. So an object here is some y to xk, which is finite tall, plus an isomorphism of y with its pullback by phi k. So phi k maps xk to itself. So I pull back along that. I get some other thing that's finite tall over xk, and I compare the two. Of course, the thing I get is, there is an isomorphism of y given by Frobenius on y, but you don't have to pick that one. So you allow all possible choices. Yeah, sorry. So I take a finite tall object over xk, and then I say, well, this is the, so to speak, relative Frobenius. This is Frobenius acting on k, but so to speak, not on x. So that's a morphism from, I can use that as, since x is over Fp, OK, this is a morphism from xk to itself. So I can pull back this cover, and then I compare it to y. So these are the objects here. So right, it really is just the these really are just the finite tall objects on the formal quotient of xk by this automorphism, or this morphism. It's not an automorphism. I should say, if at some point you want to start assuming that x is perfect, so that this thing is a, well, no, I guess no, it doesn't matter here. This is algebraically closed. So this is a, yeah, this thing has a.
So Kiran,
Yeah.
I have a question.
Yes.
If there is already a canonical choice of one isomorphism there,
Yes.
how is that different than just an object y equipped with an automorphism from y to y?
I guess it isn't. It's convenient to say it this way because I'm going to start taking multiple morphisms later, and then it's more convenient to set it up this way. But yeah, you're basically, I think you're right. This is, you can sort of untwist and reformulate this, but it's more convenient to leave it in this form.
And when you say isomorphism, is that an isomorphism of K schemes?
This is an isomorphism of X, or is an isomorphism of XK schemes. So.
So it's the canonical choice of isomorphism of XK schemes?
Oh, shoot. Do I want an isomorphism of XK schemes?
X, Y equals X.
Yes.
I mean, it's fine. If Y comes from
Yeah.
this and from something over FP, there is.
Right, yeah. So this is over, yeah, so,
But if it doesn't, then I don't think there is a canonical choice.
right. But the trick is that the theorem is that this is an equivalence.
Yeah.
So yeah, it's not a priori clear, but it turns out that this thing is actually an equivalence. So this is this is one form of what's called Drinfeld's lemma. Is that right? So you have these things, you can turn these things into these, but it's not a priori clear that there's some underlying finitile object over X, but it turns out that there is.
There's a fountain in the other direction.
So it turns out that there is a functor in the other direction given by like taking the invariant, taking, so to speak, VK invariance or something. But of course, you don't know that makes sense until, I mean, the content of the theorem is that it makes sense to do that. Right, a priori, you would try to do that and you wouldn't get anything. I mean, like if you did this on the level of rings and you tried to take phi k invariance, you might just get, like FP or something, or K. I mean, well, no, you would take the phi k invariance. You might just, that might just be FP. It's not clear that if you take, right, if say X is affine, so you're taking X and you're tensoring over FP with K, and then you have some finitile algebra over that with an action of phi k, a priori, if you take the phi k invariance, you might just get FP. It's not clear that you get something that's big enough. Well, I guess you would get, no, sorry, you get the ring, you get the coordinate ring of X back, but you might not get anything more. So you might not actually, if you go this way and then this way, you might not get back anything. But you might not get back what you started with. So the content is that, right, so sort of going from here to here and back, it's easy to see that composition is equivalence. The content is to go from here to here by taking, like say in the affine case, by taking invariance and then come back. Then you actually get the right thing here. Okay, so let me make some comments about this. Yes. Yes.
Over xk, right? Does that mean that you draw like the same, like the canonical map, X to
Yeah, sorry, I don't think I want ever X k here, actually. I don't think that's right. I mean, what I mean is, I take the, right, I mean the thing in the sense of stack. So I take this thing and I divide, so I have xk maps to itself like that. So,
that's not a map of K scheme.
which is not. It's just a map of FP schemes. So I'm saying I have a thing y here, so I want to fill in some morphism that goes here. Yeah. So that's I have the y and then the data of this map to fill it in. Right. That's all this is saying. It's just okay. So maybe I should sort of work out one concrete example that's sort of easy to. So what about if X is FP? Right. So this is already saying something when X is FP. So what about X is spec FP? So I'm saying that if I take, so I'm saying that finitile FP algebras are the same as finitile K algebras divided by this action of phi k. Well, right, if I have one of these things, so if A is a finite, say A is a finite K algebra, in particular, it's a finite dimensional K vector space. So I have a finite dimensional, so if I have some operator that's giving the Frobenius action, then this is a finite dimensional phi k vector space finite dimensional FP vector space plus this phi k action. So it's a finite dimensional K vector space plus, you can think of the phi k as giving you a semilinear phi k action. Well, these things show up a lot in p-adic Hodge theory. This is basically, these things classify representations. So this is sort of this. So then taking invariance defines a locally constant FP sheaf on spec K. So this is basically this construction is essentially Lang's PhD thesis. Well, I guess it's non-abelian Artin-Schreier theory, if you want to call it that. But the non-abelian version of Artin-Schreier theory is essentially in Lang's PhD thesis, which the kind of the official exposition of it is Katz's expose 13 in SGA 7. So when you have a finite dimensional, so in general, when you have a finite dimensional vector space over a field of characteristic P plus a semilinear action of Frobenius that defines the same data as a locally constant FP bar sheaf on spec of that field. And field can be replaced by ring or more general stuff. But here I'm in the case where it's an algebraically closed field. So of course this sheaf is trivial. And so there actually is an invariant basis. And that invariant basis gives me back the elements of A. So that's secretly what's going on when if this thing is just FP, then what I'm doing here is I'm kind of encoding this construction, this sort of non-abelian Artin-Schreier construction. So maybe I'll mention as an exercise, use a similar argument to treat the case where X is arbitrary, but the field K is FP bar. So you could do, I claim you could do something similar when K is FP bar because, well, if you give me say X is a ring, X is spec of a ring, if you give me a finite algebra over that ring tensor over FP with FP bar, well, you can realize it over some finite extension of FP, and then now that actually gives you a finite algebra over that ring, and then you have to just disentangle the effect of phi k and so on. So this strategy basically can give you the general case if K is FP bar, but if K is bigger, then you need some extra argument, which I don't want to say much about right now. Maybe I'll just say this in words. So the way you prove the general case is, again, it's enough to consider the case where X is a finite type over FP by some kind of limit argument. And in that case, you could do something like this, except what you have to do is you have to take X and take a compactification. So view it as sitting inside some projective space, and then make some argument like this, except instead of literally looking at elements of the base ring, you have to look at sections of some ample line bundle. So okay, so I should mention as a corollary, So if you want to say this in terms of products of fundamental groups, so let me take n schemes over Fp, which are connected and nice. Then there's a canonical isomorphism between the product of these pi1s and pi1 of, I take the product, and then I have to divide by n minus 1 of the Frobeniae. So I take the monoid generated by n minus 1 of these. It doesn't matter which n minus 1. It's an easy argument to show that if you put the other one in, you could sort of swap it. You're getting more or less equivalent. Sort of using the fact that you have global Frobenius on everything in characteristic P, you could show that one of these terms is redundant. So you leave it out, and then well, you need to leave it out. You don't quite get the right thing if you put in all of them. So you leave one of them out, but it doesn't matter which one you leave out. You can kind of move the choice around. And then you show that when you divide the product by these n minus 1 partial Frobenius maps, you get some stack whose pi1, well, this thing is again connected QCQS, and it has the same pi1. And that is basically a formal consequence of that version. So this came up, of course. Why was Drinfeld looking at this? Well, this somehow comes up in his work on the Langlands correspondence for GL2 for function fields. And nowadays, lots of people are interested in generalizing that point of view, as extended to GLN by Laurent Laforgue, generalizing that point of view to mixed characteristic, at least in the local setting. So this brings us to part 4, Drinfeld's lemma for perfectoid spaces. Now, I'm not going to try to say what a perfectoid space is here, but since I'm only doing this in characteristic P, this is a little bit easier. In characteristic P, so unfortunately, in order to say what these are, you have to know what it means to talk about a non-Archimedean analytic space, which is not Noetherian. So you have to use the notion of adic space in the sense of Huber. But modulo that, these are basically rigid analytic spaces, which are perfect and reduced. Well, the right way to say that is uniform. And maybe analytic, if you know what that means in context of Huber spaces. So, but let me say more concretely what you should think of. You should think of, I take a base field for rigid analytic geometry, which is perfect. So I take a perfect non-Archimedean field in characteristic P, like e.g. So I say take formal power series. Right, this is a perfectly good field which is complete with respect to evaluation. I take its perfect closure, so I adjoin the powers of T. That's not complete anymore, so I complete it. And now this is a base field which is again complete for evaluation, so I can do rigid analytic geometry with respect to this. And then I can take rigid spaces over that. But these are not going to be perfect. So what I do is I sort of take the inverse limit along the Frobenius morphism and take so you should imagine what I'm doing here is I'm doing the analytic version of going from, say schemes of finite type over a field to perfect schemes over a field. And the way you would do that is you started with a scheme which is not perfect. Well, you could take its inverse limit along Frobenius, which on the level of rings means adjoining p power roots of things that didn't have p power roots, and in the process making everything reduced because you want Frobenius to be a bijection. So you kind of kill nilpotents as well. So yeah, if you want to think about rigid spaces, you could think about rigid spaces, except that you have to kind of take inverse limits along Frobenius. I didn't actually, it might be possible to actually formulate some of this directly for rigid spaces in characteristic P. Because here, I mean, this is not a perfect scheme in characteristic P. This is an arbitrary scheme in characteristic P. But of course, it wouldn't lose information to talk about perfect schemes, because if you have a scheme and you take this inverse limit along Frobenius, you don't change the finite tall covers. So it's not really losing information to work in this perfect world. It's just really nice to work with these perfect adic spaces, because they have they're much better behaved than arbitrary adic spaces. So the theorem, so this is, so to speak, Drinfeld's lemma for perfectoid spaces, except this is sort of, this is a new theorem, is that for X a perfectoid space, so you can again talk about finite tall covers of this thing. And you could compare the ones defined over X to one defined over X times K of phi K, where K is an algebraically closed non-Archimedean field. Because I want to work in this world of adic spaces, so this thing needs to have its topology. So I claim you can take this product and then divide by Frobenius, and then you get something that has the same finite tall algebras. And similarly for products. So for example, let me just write this for two terms. And then let me start digesting the statement, because most of what I want to say in the rest of my time is sort of to kind of unpack this statement. And then I can tell you a few words about an application if I have time. Well, very few words. So what's going on in this statement? So there's a few things. So I'm not going to say much about the proof, except to say that the proof does not work the same way as for schemes. You really, so comments. So the proof is not a direct adaptation of the scheme case. But maybe I'll say again the case where K is somehow as small as it can be. So basically the smallest thing that K could be is so K has to have a non-trivial valuation. So I take a power series field, so I get my non-trivial valuation, and then I take a completed algebraic closure of that. So this case is again easy, quote unquote, but easy in the relative sense. It's easy because we know some theorem that can be used to do this. This comes from the classification of vector bundles on Farg-Fontaine curves in characteristic P. Which predates the work of Farg and Fontaine. It's an older theorem of Hartle and Pink in equal characteristic. That's all since I haven't talked about tilting yet, I'm really just setting it. I mean, I'll mention it at the end, but I'm just doing this in characteristic P, so I'm just using that. But that's still not an easy theorem. It's just that it's easy compared to it's subsets. So it's an approach. So you have an approach that works for this case that's somehow analogous to the exercise that I gave you earlier. This exercise does not extend to this more general case. So you add sort of additional elements to K by some kind of subtle ramification theory argument. Maybe that's all I want to say about technical parts. And maybe, actually, no. Another point. The abelian covers, maybe I should really say Z mod PZ covers are easy. And this is easy in the strong sense. If you just compare the Homs from these two sides to Z mod P, that's basically comparing, Art and Schreier gadgets on the two sides. And this case is genuinely easy. And so that turns out to be helpful when you're trying to do some kind of harder argument. So this case is easy-ish. This case is really easy. This is also true for schemes, by the way. So I could have given another exercise, which is to prove Drinfeld's lemma for the abelian quotients. And that's, again, a relatively easy argument. I won't do it, but it's entertaining. So I want to mention one important special case of this, and this is related to something in p-adic Hodge theory. So the key case of interest is where I take two points. So x1 and x2 are both the adic spaces associated to some algebraically closed field. And this case is actually quite interesting because, for example, so x1 times x2 in this case. So this times is over. So there is an absolute product in this category of perfectoid spaces in characteristic P, but this is in fact not quasi-compact. So for example, actually, let me make this even more specific. Actually, and let me not do algebraically closed fields. Let me just take the perfect closure of a power series field. Then this thing is basically like the disk. So I have two copies of T. I have sort of T1 and T2. So this is like taking the punctured open unit disk in one variable over the field containing the other variable. And so when you have these kind of open inequalities, this is how you get things that are not quasi-compact. However, when you divide by phi k, say phi 2, let's say, right? You're basically saying, well, identify T2 with its pth power. So if you then this thing has the homotopy type of an open line. Here I'm kind of rolling it onto itself, and I'm creating something with the homotopy type of a circle. So I'm killing this non-quasi-compactness. So this thing, and as a bonus, something that happens that didn't happen for schemes, which is that this division by a partial Frobenius actually stays in the category of spaces. So this is it's not necessary to think of this as a stack theoretic construction. In the world of analytic spaces, you can actually do this because somehow, Frobenius doesn't have fixed points like it does when you work with schemes. So, and is a genuine space. And this example shows up in some work I was doing with a postdoc of mine, Annie Carter, and we eventually listed Gergely Zabrady from Budapest. So let me just one sentence. With Carter and Zabrady, we can use this construction to define an analog of what's called phi gamma module theory. So normally when you talk about phi gamma modules, this is some construction that's associated to representations of the Galois group of a local field, a mixed characteristic. So you take some finite extension of QP, call it capital K, and you take the absolute Galois group of K, and you take representations of that on finite dimensional QP vector spaces. And this is what, and then you convert these into some other gadgets using essentially the non-abelian Artin-Schreier theory. So you go through the fact that if you adjoin, say, the p power roots of unity to K, you get a field which has the same Galois theory as some field in characteristic P. So then you could do non-abelian Artin-Schreier theory on that. So this construction lets you do something analogous for products of GK. Or if you want, you could take different Ks here. But let me just say some self-product of GK. So essentially, for example, if you have 2 copies of GK, then when you run the analog of phi gamma module theory, so you have a representation of 2 copies of GK, that converts into some module over some ring, and there's an action of 2 different Frobenius operators and 2 different gamma operators, 2 different gamma p-adic Lie groups. So it's a very pretty generalization, and this was sort of observed in a kind of direct way by Zabrati previously. So the new thing with the work with Carter is that we sort of made explicit how this links to this version of Drinfeld's lemma, but not for schemes, which is maybe why this hadn't been done before. You have to go to this world of perfectoid spaces in order to make this link. Even though we're talking about 2 points, but even when you start with 2 points, this product is, acquires some dimension. So somehow the theory of perfectoid points, which in some sense is much older, was not sufficient to handle this. One really had to go to sort of positive dimensional spaces. So the paper with Carter and Zabrati kind of shows how this Drinfeld construction is related to this kind of thing one wants to do in p-adic Hodge theory. And the hope is that now that we really understand how this works, then you can kind of generalize this in all the usual ways that one generalizes classical phi gamma module theory. So I think I will stop there.